Let's look at a two-sided hypothesis test for proportion, part 2. So this is the second example. Here again is the idea behind hypothesis testing. We have a hypothesis, which is a guess about what is true. We collect data to test the hypothesis, and we plug the data into a formula, and then use the result to determine whether or not our hypothesis is true. I have a Roman coin in my office. It's about 1700 years old. Is it a fair coin? In other words, are heads and tails equally likely? If the coin is fair, then the probability of tails is a half. Let's test the hypothesis that the coin is fair. The null hypothesis means there's no change, no difference. We represent that as h sub 0 or h naught. The alternative hypothesis means there is a change, there is a difference. We represent that by h sub a or h sub 1. In this case, the null hypothesis is that the probability of tails is a half, and the alternative hypothesis would then be the probability of tails is not a half. Again, let p be the probability of tails. The null hypothesis always has an equal sign, p equals. So it's of the form p equals p sub 0, and the alternative hypothesis, h sub a, has does not equals, or less than, or greater than. So it's going to be of the form p does not equal p sub 0, or p is greater than p sub 0, or p is less than p sub 0. So if we represent it symbolically, the null hypothesis is p equals a half, and the alternative hypothesis is one of these guys. Okay, h sub a, p is greater than a half. We would choose this as the alternative hypothesis if we wanted to test the hypothesis that the probability of tails is greater than a half. But that's not what we were told, so we're not going to use that. H sub a, p is less than a half. We would choose this as the alternative hypothesis if we wanted to test the hypothesis that the probability of tails is less than a half. But again, that's not what we were told, so we're not going to use that one either. H sub a, p does not equal a half. We would choose this as the alternative hypothesis if we wanted to test the hypothesis that the probability of tails is different from a half. Or, equivalently, if we wanted to test the hypothesis that the probability of tails is a half, which is the case here. So again, because we were not told, hey, we think the probability of tails is less than a half, and we want to test that. Or, hey, we think the probability of tails is greater than a half, and we want to test that. We weren't told that. We were just told we want to test the probability that that tails is a half. So in that case, we would choose this as our alternative hypothesis. Okay, so our null hypothesis is p equals a half, and our alternative hypothesis, well, let's clear those guys out of there. Our alternative hypothesis is simply p does not equal a half. I flipped the coin 5,200 times. It took a couple of years. The result? 2,592 tails. Okay, here's our alternative and null hypotheses. Let's calculate the test statistic z. Here, p hat is the proportion of successes. In this case, that would be 2,592 over 5,200, proportion of successes in the trial, or really in the trials. P0 is the conjectured value of p in the null hypothesis, which in this case is a half. And so when we plug all of that in, p hat is 2,592 over 5,200, p sub 0 is a half, plug everything in, and we end up with z equals negative 0.2219. So z equals negative 0.2219 is our z-score. Remember what that means. Assuming the null hypothesis is true, this is what the distribution of z-scores would look like. It's a normal distribution with mean 0 and standard deviation 1. So if we get a z-score that's between negative 1.96 and 1.96, in other words, somewhere in this range, we have no reason to reject the null hypothesis, because 95% of the time, assuming the null hypothesis is true, we're going to get something in that range. Oh, but if we get a z-score that is not between negative 1.96 and 1.96, we conclude that the null hypothesis is false. In other words, if z is less than negative 1.96, we get something out here. Or if we get something z is greater than 1.96, we get something out here, we conclude that the null hypothesis is false. Since our z-score is negative 0.2219, and negative 1.96 is less than negative 0.2219 is less than 1.96. In other words, negative 0.2219 is in this zone. It's between negative 1.96 and 1.96. Since it's in that zone, we have no reason to reject the null hypothesis h sub 0. We accept the null hypothesis. Well, actually, we never say that we accept the null hypothesis. We say that we fail to reject the null hypothesis. Now, this is going to drive you batty. It just seems so awkward. What do you mean, we fail to reject the null hypothesis? Isn't it the same as saying you accept the null hypothesis? It's like, instead of saying, I love my wife, it's like saying, I don't not love my wife. It's just so awkward. It's this circumlocution. Here's the reason we never say we accept the null hypothesis. We can't really be certain that the null hypothesis is true. It might be off by a little bit, but we don't have sufficient evidence to reject it. So rather than saying we accept it, because we don't know if it's true or not, we at least say, yeah, we can't reject it. We failed to reject it. There's not enough evidence to reject it. Okay, let's find the p-value. Recall what the p-value is. This is short for the probability value. It's the probability that we would get a result this extreme, or even more extreme, if the null hypothesis were true. In general, when the alternative hypothesis is two-tailed, that is, when it's of the form h sub a, p does not equal p0, which is what we have in our case, the p-value is twice the area to the right of the absolute value of z. So the area to the right of the absolute value of z is the area to the right of absolute value of negative 0.2219, which is the area to the right of 0.2219. When you use your TI, normal CDF, 0.2219 to 10, well, that area is 0.4122, because it's really just about everything from here on to the right. And twice that is 0.8244. So that would be our p-value. Okay, so our p-value is 0.8244. If the p-value is less than 0.05, we reject the null hypothesis, because there'd be a less than 5% chance we would obtain a result this extreme, or even more extreme if the null hypothesis were true. So again, if the p-value is less than 0.05, we reject. As Mario Triola says, if the p is low, the null must go. Oh, but that's not the situation we have. The p-value is 0.8244. That's a lot bigger than 0.05. So we fail to reject the null hypothesis. So again, h sub 0 null hypothesis p equals a half. H sub a alternative hypothesis p does not equal a half. We fail to reject the null hypothesis. There is not sufficient evidence to conclude that the coin is not fair.